Hello everyone, let's study about the potential due to an electric dipole. An electric dipole is defined as a system of two charges having same magnitude but different polarities and having a small separation between them. So this system is called as electric dipole. Conventionally, the distance between them is given as 2a, and we define a term called as dipole moment, which is given as the product of any one charge magnitude into their separation and into a direction which is from minus q to plus q. This topic has been done in the previous chapter of electrostatics. We can also write this as q into 2a vector form. This is called as the dipole moment because of an electric dipole. There are two important lines for a dipole. One is called as axial line. So the line joining the two charges is called as axial line, which is an imaginary line. Similarly, a plane passing through the center of dipole and normal to the axial line is called as equatorial plane. So even this is an important plane. So here we'll find out what is the electric potential at the 2 points. So first thing is we'll find out the electric potential at a point on the axial line. To understand this, let's consider a dipole where there are two charges called as minus q and plus q, and let the points be called as point A and then point B. Let the distance of the point, say point P, where we should find the dipole, be at a distance of r from center of dipole. We saw in the chapter on electrostatics that for a dipole, the reference point is center of dipole. We'll call this as point C. So let's find out what is the electric field at this point P. Since the distance between A and B is 2a, the distance between AC would be A and distance between BC would be A. Again here, the charges kept at point A and point B, each would create its own field. Therefore, the net field would be the field which is because of the positive charge and the field because of the negative charge, and we add them by normal addition because potential is a scalar quantity. Also, we know that the potential is given by K2 by R, where K is equal to 1 by 4 pi epsilon naught. So that in mind, let's find what is the net potential. So V plus would be KQ, the distance would be just BP plus K minus Q, the distance would be AP. But from here, BP is equal to R minus A, and then AP would be R plus A, because AP would be nothing but AB plus, AP would be nothing but AC plus CP. AC is A and CP is R, so it becomes R plus A. So putting it back here, we can take AQ as common, and what remains is 1 by BP, that is 1 by BP was R minus A, so it becomes R minus A, there's a minus sign here, by 1 by R plus A. So from this, we'll write this as KQ. Let's take LCM and solve it. So it becomes R plus A minus of R minus A by, it is R minus A into R plus A, that is equal to K Q, open the brackets, becomes R plus A minus R, minus of minus becomes plus A, so becomes plus A by this term is of the form A plus B into A minus B, that is equal to A square minus B square. So here it becomes equal to R square minus A square, and from here this R gets cancelled, and what remains is, it is K Q, there is 2A by R square minus A square. But recall that K into Q into 2A is called as P in terms of magnitude. It becomes K P by R square minus A square. This is the potential. If we consider for a short dipole, that means that it's like this is what the dipole is. This is like minus Q and plus Q, and the point P is very far away. So in such case, the distance R is very small. So this R is small than the R involved here. In such case, we can say A is less than R. It means A square is very much less than R square. Therefore, R square minus A square is almost same as R square only. So with that in mind, we put it back here, we get V is equal to K P by R square, or it will be P by 4 pi epsilon naught into R square. So this is the required potential because of this dipole at a point on the axis. Let's find out what is the potential at a point on the equatorial plane. So again, let's redraw the configuration where we have charge minus Q and then plus Q. So a plane passing through center is called equatorial plane, but from side view we just see a straight line. Suppose this is the point P where we need to find the electric potential. Now distance from here and this would remain same. For example, if this point is called as A, this is B, the distance from A to P is same as B to P. So net potential is equal to, it will be because of plus charge and then minus charge. Here V plus is equal to AQ by AP. Now this distance is A, this also is A, and this distance from this point to center, let's call it as R. Now AP and BP would be same, and V minus is equal to AQ by BP. If we add them together, the net field, which is V plus and V minus, is equal to, this minus sign here because minus Q, it will be K Q by AP minus of AQ by BP is equal to 0. So the electric potential at any point, that's a point somewhere here or here or here, at any point on the electric, on the equatorial plane, the potential is 0.